Hello, everyone. I'm Ed Pegg Jr., and we'll be starting very shortly. I'm going to wait for my clock to tick to 11 here. And welcome, everybody. I'm Ed Pegg Jr. from Wolfram Research. And today we're going to be talking about 2025 and other numbers and the online encyclopedia of integer sequences and their connection to Martin Gardner's mathematical games. This series has been a homage to Martin Gardner and mathematical games. He wrote a column in Scientific American for 25 years and produced 15 books on various mathematical topics. And that helped to inspire many mathematicians, including myself. So this series has been sort of revisiting various things that Martin Gardner talked about in his columns. And one thing he did frequently was look at a particular year or number and find out interesting properties for it. And we have many demonstrations that go into detail about various types of numbers. And I'll be showing some of those today. So let's start with 2025. We happen to be in this year. And one property of the year is that it's a sum of the cubes of 1 through 9. It's also the triangular number 45 squared. So this leads to something called the partridge problem. And it's based on the days of Christmas, 4 calling birds, 3 French hens, 2 turtle doves, and a partridge in a pear tree. That sort of thing where the smallest item is used very infrequently. There's 1 1, 2 2s, 3 3s. That's one way of slicing up a cube. So if you have a series of cubes, you could slice these up into unit stacks, and it turns out you can rearrange these in order to make a size 45 square. 9 times 5 is 45. So this is one way of dividing up a square of size 45 squared, or 2025, into a cube. You could rearrange these into a order 1 cube, order 2 cube, and so on. So the sum of the cubes is equal to the square of the sum, which is Faulhaber's formula, or the Nicomache theorem. The sum of the cubes is equal to the square of the sum. And here's another solution for that. Here's a more common way this is shown, where you split the even squares in half. This is a proof without words for the theorem. And here's a way of doing it with Cuisinart rods. We can also stack cubes together. It turns out you can also do this with triangles. And it happens to be that squares, the smallest order possible that you can solve this problem is order 8 for the partridge problem. And you can see that here we can just strip out the 9s, and we have an order 8 solution where all the squares are whole. Order 8 is the smallest solution possible for squares, but other shapes have smaller possible solutions for the partridge problem. One particular one is the 30, 60, 90 triangle. That one is order 4. So if you have one half equilateral triangle, or one 30, 60, 90 triangle, and you have another that's size 2, another 2 of size 2, 3 of size 3, and 4 of size 4, you can rearrange those to get a size 10 30, 60, 90 triangle. And that's a very good puzzle. The solution is unique. And that is one of the smallest partridge solution problems. The equilateral triangle itself, though, is order 9. and this is the smallest solution. But there's other properties for 2025. For example, it is the product of its proper divisors. These are the proper divisors. When you multiply them together, you get 2025. You can also express 2025 in this way. If you take a look at the smallest integer triangles that all have the same circumcircle, for order 8, these are the smallest different circles, and it turns out that the circumference of all of these is the square root of 2025 over 11, and these show these 8 triangles here. We also have this rare property with divisor sigma and Euler phi for the cubes of 2025. The repeating decimal for 1 over 45 is a series of 2s, and it's the denominator for this sum of squares, 9 to the minus 2 plus 5 to the minus 2. We can also represent it in the fine number system like this. And when we raise these to the golden ratio and add them, we get 2025. A good permutation is one where all rotations of it, for example, this is a good permutation at the top, and we can rotate it in various ways so that only the single digit on the diagonal is the correct one. All other digits are incorrect. So this is the first of the good permutations, and it turns out there is exactly 2025 of them. It's the product of greatest common divisors less than 15. It's the sum of 2 high powers, 3 to the 6 plus 6 to the 4th, and it's self-descriptive. 20 plus 25 squared is 2025. I'm not sure where I got this, probably somewhere in online encyclopedia of integer sequences. And a final neat property is that if you add 1 to all digits, you get 3136, which is also a square number, 56 squared. So these are some unusual properties of 2025. There's also a lot of graphs that have graph properties that equal 2025. For example, the minimal total dominating set count of this graph is 2025. And if you'd like to take a look at these, there's going to be a community post sometime today that has all of this in it, in case you'd like to look at any of these more closely. Last year, we did this as well. These are some of the things we found about the number 2024. It's the Chebyshev T of 3, 8. It's also this particular sum of the digits 1 to 9. It's a binomial number. What else did we find? It's a convergent for the square root of 3, 2024 up here, which leads to this unusual property. And it's also a dodecahedral number and a tetrahedral number. So this object here has 2024 spheres in it. And the division lines here show how it's also a dodecahedral number. We did it in 2023 as well. And these are some of the properties that we can reach with 2023. For all of these, we could also put a number into Wolfram Alpha and find some unusual facts about the particular number. So here I do it with this number, 11,121,217. And it turns out we always give the residues of a number And when you do that for 11121 the residues in the various moduli are 111 It's a self-reflective modulus number, and we can check that by looking at the moduli 2 to 9, and we get the same digits. And it turns out that this is a integer sequence in OEIS. And here are more numbers that have this property. This is the last one known. If there's any other numbers that have this property, they're greater than 10 to the 30. So if anybody would like to search for other numbers that have this property, it's an open problem. So Martin Gardner introduced the original book for integer sequences in a column on Catalan numbers. He also mentions other sequences, powers of 2, the squares, Fibonacci sequence, triangular numbers. And he mentions all of these are in the 1973 book, A Handbook of Integer Sequences by N.J.A. Sloan. And we can generate the Catalan numbers like this, or also like this. And the index for Catalan numbers in OEIS is 108. And as Gardner mentions in the column, it was Euler that first wrote out the Catalan numbers, looking to see how a polygon can be divided into non-intersecting triangles. And he found the sequences 1, 2, 5, 14. And then he came up with a formula for how to generate that sequence. So we can see for various polygons, the various ways that they can split up. Like so. Like so. And we can look at the code for this and generate. We can find out how to generate these. So these are the 49 ways of dividing up a nonagon, which I mentioned last month might make an interesting card set. A earlier item that Gardner discussed was folding stamps in book 6. So these are the different ways of folding up a strip of stamps. There's just one way of folding up 2 stamps, 2 ways of folding 3 stamps, and 5 ways of folding 4 stamps. And he asked how many different ways you could fold up 5 stamps distinctly. And it turns out there's 14 ways. The cover of the original book for OEIS has these stamp representations on the cover of the book. The generating formula for this is still unsolved. This is the last term that's known. So this is another open sequence. Gardner also talked about primes quite a bit. He talked about the Golomb spiral, which is here. Solomon Golomb was in a boring meeting and he started writing out the numbers in a spiral on a sheet of paper, like so. And he was still bored at the meeting, so he started indicating where the primes were, and he noticed that they started to make strange patterns. So that's what this demonstration does. It highlights the primes in a growing spiral. The ternary system was another thing that Gardner talked about, the ways of representing numbers in different bases. He also talked about the binary system. The ternary system allows for a way of measuring a certain weight. For example, here's how to weigh a 25-pound object. We have the object here. We have 27 plus 1 here, or 28. And then on the other side is 3. So 25 plus 3 is equal to 27 plus 1. So this is a way of weighing a 25-pound object. And this leads to what's called the balanced ternary system. And I show that here. So here we can measure a weight weighing 2. We have 3 on one side, 1 plus 2 on the other. And we can keep doing that. So 1 here means it's positive. With a underbar, it means it's negative. So here we have the fourth position, or 0, 1, 2, 3. You have 3 to the third on this side. And since these are minuses, we've got 3 to the 2 on the minus side, and also 3 to the 1 on the minus side to measure 15. And all weights up to 40 can be weighed with these 4 weights and balanced ternary, or 5 weights, since we're going up to 81. Let's stop that. Okay. The various common sequences everybody should know are the square numbers, the factorials, triangular numbers, and then there's stranger sequences such as the centered hexagonal sequence, which is if you put coins in a triangular array and you make hexagons, this is the number of coins you'd get in a order 2 hexagon, order 3 hexagon, and so on. The 5 smooth numbers, here I give a range. These are numbers where the greatest prime divisor is 5 or less. We can take a look at perfect numbers. Just sometime in the last few months, the next perfect number was found when the largest prime number was found, a new Mersenne number. And you can generate a perfect number from a Mersenne prime. Whether there's any other way of generating a perfect number is unknown, and that's where the sum of proper divisors is equal to the number itself. For an amicable number, the sum of the divisors, not including itself, is equal to another number, and if you repeat the process on that number, you get the original number. So, for example, 220 and 284 are amicable numbers, and these are the lowest amicable numbers here. If I did this set here again on these numbers, we would get back this original set. So, for example, 1184 and 1210 are amicable numbers. If you get a chain of numbers, they're called sociable numbers. And here's his column where he talks about these. He also talked about Fibonacci numbers and Padovan numbers. And you can generate these for Fibonacci numbers by making a order 2 square, adding a square, adding a square, adding a square, and so on. You get what's called the Fibonacci spiral, and that generates Fibonacci numbers in a spiral. But you can also do that with triangular numbers, and you get what's called the Padovan sequence. So here we have an initial set of triangles, and when we keep adding more triangles, we get the Padovan sequence. 1, 1, 1, 2, 2, 3, 4, 5, 7, 9, 12, 16, That's the Padovan sequence. He also talked about Armstrong numbers without mentioning that particular name. That's the numbers where the sum of the digits to a particular power is equal to the number itself. For example, 1 to the fourth plus 6 to the fourth plus 3 to the fourth plus 4 to the fourth is equal to 1,634. Here he's listing the various numbers that have the various properties. For example, 1 cubed plus 5 cubed plus 3 cubed is 153. So in his Dr. Matrix column, he talks about these numbers, but he didn't know these were called Armstrong numbers. And this particular link doesn't know that Martin Gardner mentioned all these in a Dr. Matrix column. So I plan to go to this sequence and add it once I'm done with this talk. The last, there's only a finite number of these that are equal to the sum of the powers. This is the last one. This number, you can add powers. I forget what power it is, but if you add up the powers of all these digits, you get this original number. For the binary gray code, you're basically wanting this property where you have a series of numbers that don't change much from one to the other. You're basically arranging them so that only one bit of the binary representation changes with each step. So in normal binary numbers up here at the top, a lot can change in one step. One way of generating these is to take, say, a cube and put the binary representations as coordinates on each vertex, and then try to find a Hamiltonian cycle that goes through all the points. One way of doing that is to use bit XOR in this way, and this is the classic gray code. But it turns out there's multiple ways of doing this. For a cube, there's 12 different Hamiltonian cycles for the cube. The hypercube, there's this many. However, it's unsolved what the next one is for, let's see, 3, 4, 5, 6. It's unknown what number of gray codes there is for the 7 cube. One application of these are used on satellites. There's a light sensor similar to this, and a small slot when a starlight comes in through that sensor and hits the detection array, the changes are very small. You'll know that instead of jumping around a lot like you might see up on the top one, the number changes for the relative brightness is a very small change in each case, because only one bit changes at each step. So you're able to get a much better angle with this sort of light sensor than a more chaotic one, which is based on a pure binary sequence. Crossing numbers is another unsolved case. In World War II, a lot of mathematicians were rounded up and put into work camps. One of them was Paul Turan, and while they were trying to work him to death at a brick factory, he noticed that the carts moving bricks around had to go on these tracks and rails, and the biggest problem was when a cart had to go over some of these rails, and bricks would fall out, and the various workers would be punished for that. So he came up with a way of reducing the number of these crossings in order to get less punishment. And he managed to get scraps of paper and wrote down a theorem about these crossing numbers, and managed to get it smuggled out of Germany and published while he was still in one of these work camps during World War II. Palteran. And part of this column talks about crossing numbers, which Palteran came up with the mathematics for. One of the things I did was find the smallest cubic graphs that had various crossing numbers. The Peterson graph is one of the smallest graphs with 2 crossings, for example. The utility graph is one that has 1 crossing, and the tetrahedral graph is the smallest cubic graph with no crossings. But it turns out that many of these graphs are interesting. For example, the Coxeter graph is one of the smallest with, I think, 10 crossings. And the Tut cage is the smallest with 12 crossings. And almost all of these graphs turned out to have interesting properties. The Desargues graph, for example, is one of them. So I did a column about all these various crossing number graphs, and now it's a standard thing, the crossing number graph. But we don't know what is after the Tut 8 cage. Polygonal numbers, if you just if you start by adding just 1 at each step and then taking the sums, 1 plus 1, 1 plus 2, 1, 2 plus 2 plus 3, you get the triangular numbers. Square numbers, if you skip 2 each term, 1 plus 3 is 4, 1 plus 3 plus 5 is 9. The next would be 16. Those are the square numbers. So based on triangular numbers and square numbers, they extrapolated that to pentagonal numbers and hexagonal numbers. And there's various formulas for each of these. The pentagonal numbers are this sequence, the hexagonal numbers are that sequence. And here we see initial terms of each. One other that he talked about, Martin Gardner, was the Withoff sequence, NIM sequence, which is a winning new moves in a particular game. If you pair these numbers up, 1, 2, 3, 5, 4, 7, these are particular winning pairs for a chessboard-based game, a positional-based game. Here's one of the oldest sequences in OEIS. Ames, a scribe in 1650 BC, wrote down this sequence as the first digits for Egyptian fractions. And he mentioned that Ames mentioned that he was copying this very, very old sequence from somewhere else. So there's a lost document that this papyrus was referencing, and that's one of the first mathematical references in all of history as well. So he talks about Egyptian fractions here, and the rule is for Egyptian fractions is that only fractions with a 1 on top were allowed. So if you have a particular number, for example, 346, the Egyptian way would be to take 1/16 and add 1 over 386. So the fraction 346 would be represented as 16 and 368. That was the way the Egyptians like to do fractions. And it turns out there's many weird things, many weird properties of Egyptian fractions. They can get strange very quickly. For example, here's how to do 293 over 1595. You need all of these if you do it the greedy method. But often, and the greedy method is to take the largest possible fraction to start with, and then the next largest fraction you can find, and then to keep doing that until the number runs out. That's not the optimal way of doing it. There's better ways than the greedy method, but since it can get so strange, the greedy method is often the one that gets used for Egyptian fractions. One open question is how many fractions are needed? Can you always represent 4 over n with just 3 fractions? And oops, let's see if this actually works. Okay. So here's 4/15, and it turns out there's 39 solutions. And here's 5/15 or 1/3. Let's find a prime number here. 41. There's 7 solutions for 4 over 41 with a 3-part Egyptian fraction, and there's 6 solutions for 5 over 41 as a 3-part Egyptian fraction. It's unsolved whether 4 over n and 5 over n can always be done as a 3-part Egyptian fraction. That's a long open question, and it's strange that something as simple as fractions from 4,000 years ago is still unsolved. That's a problem Ames was working on. More on fractions. We can use a sequence to generate any proper fraction. For example, 3 over 6 is not a proper fraction because you can divide both the top and bottom by 3. But if you look at all proper fractions, somewhere in the Calkin-Wilf or Stern diatomic or Fusk sequence, there's a neighboring pair of numbers which give that particular fraction. The Calkin-Wilf enumeration begins like this: 1 over 1, then it adds 1 to the top and bottom, and then it branches like a tree. That's what's called the Calkin-Wilf sequence. And notice that the denominator here is the numerator here, and so on. 2 and 2, 1 and 1, 3 and 3. So just the series of numerators gives the Calkin-Wilf sequence, which is this here. And so for any particular integer, there is a corresponding Calkin-Wilf fraction and a corresponding Stern-Brokat sequence. For example, these. And I forget if Martin Gardner talks about the diatomic sequence. But this is the, may as well show this. This is what the sequence looks like on OEIS. One I mentioned in the last talk is the Singer difference set series. So the series 7, 13, 21, and so on up to 133. And it keeps going. These are the ways of making a circular wheel that represents all values. And let me show it for this difference set, for these 4 values. Every number from 1 to 13 is represented in one of these differences. For example, between this dot and this dot, the length of the arc is 1. Between there and there, the length of the arc is 2. Add those together, you get 3. From here to here, you get 4, and so on. Every single possible difference from 1 to 13, and here's 13 on the outside. We go the other way. From this to this, we go the opposite direction. And it was Singer in the 1930s that first found these series of different sets, circular different sets that always work. And there's a lot of nice mathematical properties that these have, and I talked about these last month. However, this particular series is identical to the maximal index of the maximal subgroup of this particular group. And it's only been verified up to this value, but it's they're identical so far. And an open question is whether this sequence for the different sets is identical to this for the maximal subgroups. It's an unsolved question. A common problem is if you have a cake or pancake or something, what is the maximal number of pieces you can cut it into? It turns out with one cut, that's pretty simple, and with two cuts, that's also simple. It starts getting more complicated with three cuts. The maximal number of pieces you can get is 7. And for 4 cuts, the maximal number of pieces you can get is 11. So that is this sequence here, the pancake cutting sequence. And you basically want every single line, every single cut to intersect every other cut. And that's how you make sure you maximize. One other thing you can do with pancakes is you can flip them. And the description of the problem is the chef in our place is sloppy, and when he puts down a stack of pancakes, they're all in all different sizes. So before he delivers those to a customer, he'll take a spatula and start flipping the pancakes, repeating that until all the pancakes are sized in order on the plate. And the question is, what is the minimal number of flips necessary to sort a stack of pancakes with flipping? And you get this particular sequence. For order 19, for 19 pancakes, this is the maximal, this is the maximal number of flips. It needs 22 flips for this particular set. The worst set for order 20 is unknown. Sorry about that. Now, one curiosity about this problem is that a paper on this, on prefix reversal or flipping pancakes, one of the first major papers about this was written by Bill Gates of Microsoft. It's his only mathematical paper. Another unsolved problem is the minimal sorting networks. This is as far as we know for the sequence, and here's an illustration of terms. We basically want a perfect sorting network. So for any sequence of digits, if you make that series of comparisons, you'll get a perfectly ordered set at the bottom. So for 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 items, the minimal number of comparisons you need to do to make sure you always get a ordered set at the bottom, you need 39 checks at the end. And these are diagrams of the possible checks you can do for these perfect sorting networks. What the next one is unknown. Now, one thing I usually do at the end of these talks is I'll mention open questions that no one has solved yet. This time, almost everything I'm showing in this talk is unsolved. I have always liked unsolved questions, especially those that might be approachable. Now, quite a few of the items that I've looked at, I thought, well, maybe with a computer I could solve that. Many of these problems were looked at in the 50s, 60s, 70s, or earlier, before any computers were available. And today we've got 100 trillion times more computing power available than was available to early mathematicians. So if we can write a clever program, often it's the case that we can solve a question which would have been impossible in the 1500s, for example. So here's a sample unsolved problem. We want the least k so that the members of the set, each subset has a distinct sum. And we want to know the lowest value for the highest term. For 9 numbers, this set of 9 items, all these pairs have distinct sums. So the distinct sum problem solution for order 9 is 161. It's unsolved what the value is for order 10. Now, I think I could probably solve this one because I solved the sparse ruler problem, which is very similar to this. So if I wanted to solve this, I would probably look at these initial terms and write up a flip-flop routine where I basically make small changes to the sets, and I run that 1 trillion times, where I save the sets that work and throw out the sets that don't work, but I'll vary them and see if I can produce new sets of the sort. And I just let that run overnight on 8 cores to do 100 trillion calculations, and chances are good I'll find something new if I make that run. But pretty much anybody can do that. So these are interesting problems to throw programs at. The polygon square dissection, I talked about that. I think talk 8, I think. But it's unsolved how the sequence progresses from there, and only a few of these have been proven. The haberdasher problem I mentioned, I think 2 months ago, it's finally been proven that you need 4 pieces to divide a regular equilateral triangle into a square. I believe the rest of these numbers, except for the square, are unproven. But it's believed that these are the best solutions for the minimal number of pieces to divide a polygon into a square. Schur's number, you want to take a sequence and color all the digits from, say, 1 to 44, so that you can't do x plus y equals z within a particular set. So here's a solution here showing how you can four-color up to 44 so that you never get a single color version of x plus y equals z. So in this form, x is able to equal y, and you get this series when you minimize those. If a plus b plus c does not exist and all 3 are distinct, you get a different set. And here's a order 4 solution here, going up to 66. They've got a solution for 196, but it's not proven. And what the next one be in the sequence is unknown. So that's the Schur number problem. And these are the 2 links for those. The no repeated distances problem is you want lattice points so that all the distances are unique. So for example, we can take a look at 16 points, and these are all the unique distances between them. These are not proven, but it's believed that these are the best solutions. And we haven't gone beyond 26 points yet. The maximal length of an uncrossing night path. Here's solutions showing up to 35. That's for the order 8 board. There's 35 night moves in a non-crossing path. And that's the solution here. Various people thought that 47 was the maximal for a 9x9 board. One of those people being Donald Knuth, and Knuth managed to prove that his solution for the 9x9 was correct with 47 moves. The largest night path that doesn't cross itself for the 10x10 board is unsolved. And since that one's hasn't been looked at seriously for about 20 years, I'm pretty sure that one could be solved pretty easily today. Maximal queens on a board, so that each one attacks only one other. So this is the for how many queens is that? 6 plus 6 for 12 queens on a 9x9 board. This is the unique solution for each queen attacking exactly one other. And this was a question in, I believe, the last Recreations. Peaceable coexistence of armies of queens leads to a series of strange solutions. This is as far as the sequence is known. Sequence 25 or 250,000 leads to this sequence here. And these are what are believed to be the next terms, but none of them are proven. For a maximum no square grid, what's the maximum number of points you can put into a grid so that you don't get a square? And there's two versions of this. One, you're only looking at squares with edges parallel to the sides. And this is a solution for the 9x9 board. They know it up to, I believe that's 13 by 13 board. And if the squares can be in any orientation, it gets more complicated. You can have fewer points in those grids. But for there, they've only solved it up to order 10. The solution for order 11 is unsolved at the point. And here's a solution for that where none of the 4 points makes a square. For powers, so that there's two solutions for the same thing. For example, 1729, or the Ramanujan taxi type number. It's the sum of cubes in two different ways: 1 cubed plus 12 cubed, or 9 cubed plus 10 cubed. The term for fourth powers is here. There's two different solutions for the sum of fourth powers, but what the next term is for the sum of fifth powers is unknown. And that's the sequence here. And there's a related sequence of the sum of 3 nth powers in at least two ways. And these are the known solutions. And these are all the known solutions. What the next term is for 7th powers is unknown. I find it unusual that this one has not been solved or extended. The smallest cage graphs, the girth of a graph is the shortest cycle. So for the Peterson graph, the smallest cycle is 5. Here, the smallest cycle is 6, 7, and 8. This has only been solved up to girth 12. The smallest cage for cubic cage for 13 is currently unknown, but they have bounds for it. For solving a sliding block puzzle for a 5x5 or for a 4x4 sliding block puzzle, the minimal number of moves is 80. It's unsolved for a sliding block puzzle on a 5x5 what the minimal number of moves is. And that seems like something that should be solvable. The bounds on it are pretty high at the moment. There's a lot of unsolved problems with determinants. For example, if you arrange the numbers 1 to n and a 1 to n squared in a grid, what's the maximal determinant? Here's the maximal determinant for 1 through 9. And that's been solved up to this order. but for pretty much any problem with maximal determinants or determinant zero or the Hademan matrices, uh, there's eventually a set where they just don't know anything about what the determinant might be. Dedicant numbers were recently extended. They found this for the number of simple games in a particular set of rules. It was unknown what the next one would be. Here's one way of representing the various variations of this, and these Boolean functions have these variations up here. That these are, I believe this corresponds to Boolean number 10 or Dedekind number 10, but it's unsolved what the next term would be for this. So one thing I'll need to face next year is what interesting properties 2026 might have, but I don't plan to think about that too much until December. However, one way I found many of these things relating to 2025 and 2024 and other numbers is to look at the online encyclopedia of integer sequences and find the number and basically read through each one to see what the more interesting sequences are that have that particular number. So that's what I had. If anybody has any questions, I'll be glad to answer them. Anybody have anything? Feel free to type into the chat. And I think that can wrap it up. Many thanks for stopping by.